John. I'm glad to be here. I was here, I think, a little over 10 years ago, maybe 12 years ago, where I talked about relay channels. That was a hot topic at that time. Since that time, around 2006, I got involved in optical fiber work at Bell Labs, and the main partner that I was working with was René Jean Siombre, who is still there. This talk is going to be about optical fiber. Now, optical fiber is something that really comes from the realm of the physicists. So they are really the ones who moved communications forward inside optical fiber. And I think it's somewhat remarkable that some of these topics didn't get a lot of attention from the communications community, the electrical engineering and communications communities, until perhaps maybe 10 years ago, which I still think is rather remarkable. So I'll be talking a little bit about that, and perhaps we'll think about why that happened. So this is also based on joint work with Mansour Yousefi. Mansour was a PhD student of Frank Shannon at the University of Toronto, and he came to Munich to do a postdoc as part of a funding provided by the Thom Institute for Advanced Study, which is a new center within the Technical University of Munich since about 2006 or so. And Mansour has now just started his job a month ago, I think, or maybe even at the beginning of this month at Telecom Paris Tech as an assistant professor. And Frank is, of course, at the University of Toronto. So, to talk about optical fiber, let me begin with my main message. So that's what I'm going to end with, and that is a bound. So if you're doing information theory, you like bounds, right? And what I have here is an upper bound on the spectral efficiency of a standard optical fiber model. I'll be explaining that model. And if you look at this upper bound, it says that the efficiency in bits per second per hertz, the number of bits per second per hertz that we can transmit over a standard model, is upper bounded by log of 1 plus the signal-to-noise ratio. Now, for those of you who know the additive white Gaussian noise channel capacity, you'll recognize that and say, well, that's just the additive white Gaussian noise channel capacity. So, however, for the optical fiber channel, as I'll show you, this is a trickier channel. And as far as I know, and I think it is true, this is really the very first upper bound on the capacity in optical of a full model, and I'll explain what I mean by a full model of the optical fiber channel. It turns out that the bound is tight at low signal-to-noise ratio because the channel operates in a linear fashion at low SNR. But at high SNR, it's a very non-linear channel, and there this bound could be very loose, or it may not be.
That's exactly what I want to ask. Maybe they didn't mistake the question, but the main feature of the optical channel is non-linearity.
Yes.
You account for it in non-linearity.
I will explain that. So when I will account for it, and that's what I'm emphasizing with the word full, but I'll come back to that there. So this bound, most people believe, and I believe, this bound is very loose at high SNR. Although I could say more about those, there are some tricks we can talk about, but I do believe it's very loose. In fact, the best lower bound we have at high SNR is one that goes to 0 as the launch power gets large. And there, I'll explain why I believe, and also many other experts believe, that this is actually a valid statement. But we don't know. And I will say, though, even at high SNR, it's better than having infinity as an upper bound. So I think that's not bad. Okay, so what I'm going to do now is go through some preliminaries to just basic information theory. I think that's in the comfort zone of most people here. Then I'll talk a little bit about the history of optical fiber, talk about the channel model, and then we'll start developing this upper bound. Okay, so let me talk about, first, to talk about the spectral efficiency and capacity, of course, we have to work with information theory. So most of this should be familiar to, I'm guessing, almost everyone in this audience, but perhaps not everyone. So, okay, we're going to talk about entropy and mutual information. Consider, for example, a pair of random variables with some joint distribution. The entropy is the expectation of minus log of the probability distribution of that random variable with respect evaluated. Taking the average here, expectation is with respect to the random variable. So these two x's play a different role. That x is a label, this is the random variable. We can talk about conditional entropy, where we simply take the average overall conditional probability distributions. And mutual information is then the difference of these two entropies, and it turns out to be a symmetric quantity. We talked yesterday a little bit about directed information. Mutual information has no direction because it's just based on joint probability distribution, so we can swap x and y and get the same answer. Now, if x is a continuous random variables, this is for discrete random variables. For example, Gaussian random variable, then appropriate entropy is called a differential entropy, and we usually use a different notation for that. So for example, if we look at Gaussian random variables, the entropy of a Gaussian random variable with variance given by this quantity here is 1/2 log 2 pi e variance of x. The conditional entropy, we have to multiply that term by 1 minus rho squared, where rho is the correlation coefficient of x and y. And then if you take the difference of these two, you get the mutual information between two Gaussian variables. Looks like this, 1/2 log of 1 minus rho, 1 over 1 minus rho squared. For example, if rho is 0, then we get log of 1. Of course, the mutual information is 0 for a statistically independent random variable. On the other hand, if rho goes to plus or minus 1, this thing blows up, which may sound surprising, but of course, a continuous random variable is ridiculous. It's not a real quantity. It's the real numbers aren't real. It has infinite precision, so of course the mutual information between infinite, or the entropy of the infinite precision variable here is infinite. So it shouldn't surprise you that this blows up. That's the correlation coefficient. Okay. Then we talk about Shannon's channel capacity. So the capacity C of a channel with an input x and output y is the maximum mutual information under constraints put on this pair. For example, the most common example is the real alphabet additive white Gaussian noise channel. Y is x plus additive white Gaussian noise with variance n. And usually we talk about only an input power constraint. So the second moment of x is at most p, and then you can show that the mutual information is upper bounded by 1/2 log of 1 plus s and r. Perhaps a more common example of this is to work with complex alphabets rather than real alphabets, because we have passband channels and we take the sinusoid component as orthogonal to the cosine component, so we can view that as two parallel channels, and we just multiply this number by 2 because there's two parallel channels, so it turns out to be log 1 plus s and r. And for complex alphabets, the noise power is usually taken to be some constant and 0 times the bandwidth. So the more bandwidth you consume, the more noise power you're taking into your signal. So M naught here is the one-sided noise power spectral density. And that is the bandwidth. And if we compute spectral efficiency, what we have to do is we have to take this capacity and divide it by the bandwidth. And it turns out that those numbers become the same if we use so-called sync pulses of bandwidth W. So that's what Shannon did. And then these two numbers become the same. If they're not, if you don't use sync pulses, of course, then the spectral efficiency will be smaller than the capacity, so more bandwidth. But it's important to take all dimensions into account when normalizing. We shouldn't forget that. And in fact, in this area, as in other areas of communications, you always have to be cautious. Often when people talk about spectral efficiency, they talk about capacity without normalizing properly. Or if they talk about capacity, they mean spectral efficiency. And so these terms get mixed up a lot. So you have to be cautious, and that happens a lot in optical fiber literature. Well, I'll come back to that later. Just to plot this curve, here is this log of 1 plus s and r plotted against the logarithmic scale. The usual one is to plot this as the energy per information bit energy divided by the energy of the noise. It's in a way that this is watts per hertz and not. And then if we plot this, we get a linear curve at high S and R, because we're plotting it against the logarithmic scale. There's the optimal, there's the capacity. If we use non-Gaussian signals, then we get lower capacity. A typical one to look at is quaternary phase shift where you're upper bounded by the number 2. And if the noise and signal power are the same, we get a 1 bit per second per hertz. Here C is the same as 8 beta. Now usually we talk about two general regimes. The the energy efficient regime. Energy efficiency is related to the slope of this curve, and the slope is maximum down here, so that's the energy efficient regime. Out here, we're energy inefficient or power inefficient, but we have high rates. So I'm going to be concerned primarily about this regime. Okay? That's where nonlinearities start entering the picture. When you pump something with such high power, you can't model the channel as linear anymore, which should make some sense. I mean, if you have small variations, things are linear, right? A natural model is one maybe simple explanation of why the most channels we look at are linear, because we're interested in sending with little energy. With optical fiber, it's different, right? We don't have an energy constraint. As such, we can pump as much into that thing until it melts, right? We don't really care, right? And that's actually what happens when you send data over thousands of kilometers through the ocean or across the continent. And in fact, the energy we pump into a little thin hair of fiber, if you look at the surface area, the power per surface areas is hotter than on the surface of the sun, just because it's such a small little piece of glass and it's pumping so much energy. And so when that happens, strange things happens with the atoms, with the electrons. They can't react as fast anymore. They're being pushed too far out to come back again, to swing along with the signal, and that causes phase shifts in your measurements. At least that's how it's explained to me. I'm no expert in physics, but they talk about inelastic behavior of the particles at these high energies, and that's what causes nonlinearity. Okay. Oh, good. I forgot that this comes in one by one. Anyway, in case you have any questions, please feel free to ask. So I'm going to come now to the next part of the talk and just give a brief history of fiber communication. I get all these things from my colleague, so he's an optical physicist and very much into this topic. So if we look at fiber communication, perhaps one of the most important milestones is the invention of the maser. It's the same thing, same principle as laser, just at much lower frequencies. So this was invented first, so probably one of these, I don't even know who these people are. One should be Jim Gordon, and the other one is probably Charles Towns, but I'm not sure. And I should know that Renee should know. So this was invented at Columbia University. Jim Gordon was a person who's not as well known, I think, as Charles Towns, who won the Nobel Prize, but he's one who's played a huge role in the development of fiber optics. He passed away, I think Charles Towns just passed away a year ago or something, and Jim Gordon as well, so both of them passed away recently. So they were both at Columbia University. Jim Gordon was a student there, so he built the first laser, microwave amplification by stimulated emission radiation. The laser came a little bit later, and that won the Nobel Prize. It could have just as well gone to the maser, right? It's the same principle, just a different. Oh, and I should say something. The maser played a very important role in a very important experiment. So background radiation, which was discovered around this time, also won the Nobel Prize. That required the maser to get to build the low noise, they needed to build a low noise amplifier to make sure whatever they were measuring from the sky was really noise. They needed to make sure it wasn't the noise from the devices. And the device that was very crucial in bringing down that noise level to be able to measure the background radiation with precisely was the maser. So it played a crucial role in two Nobel Prize winning inventions, the laser as well as discovering background radiation. A very crucial piece. In some sense, so Renee is a big fan of Jim Gordon. I met him personally at Bell Labs, I think in the late 90s and early 2000s, and he always said he should have won the Nobel Prize. Low loss fiber was developed around the N60s, another Nobel Prize. So Charles Cow received the Nobel Prize for this relatively recently. At this time, at least from what I'm told, again, I'm no expert, but at that time the loss in fiber was so large, it was around 20 dB per kilometer, which would have not worked for carrying information so far. But Cow had the vision that that loss would come down, and eventually did. And where it is today is around 0.2 dB per kilometer for standard single mode fiber, and that's what makes the internet work. that happening, we would not be able to send and receive so much data across the world. It played a very central role in the entire internet revolution.
What is shown in that curve there?
Which here, this?
Yeah.
This is the loss as a function of frequency or wavelength here, 1 over the frequency. So, unfortunately, I don't have a bigger picture of this. It's a good question. Maybe I should blow that up at some point. This is the wavelength. What happens is you have little peaks coming in that certain molecules that are in the glass that people can try to get rid of. And in fact, so the different curves are different fibers designs. The one with the peak is an older design. The blue you see is very flat. I think that's the all-wave fiber, so that was an invention. At Bell Labs, I think they work a lot with Corning. Corning used to be, I think, part of the big AT&T thing. And they're really, it's amazing what they can do with glass. They can do all sorts of things. And this is an important point also in this area. The channel is something you can change, right? You can design. Now, there are certain, and so when you come to the question of what is the capacity of optical fiber, one really has to also ask the question of what kind of fiber are you using, what are the limitations, and so on. And those things can change over time. And they did change over time. I'll say something about that in just a second. So one thing that was also invented at some point was called Raman amplification. So fiber is a weird, thing. Because it's a nonlinear fiber, I'll show you the equation in just a moment. What you can do is something you can never do with, say, the air. What they do is, because you have nonlinearities, the nonlinearities make frequencies couple. Now frequencies don't couple in linear media. So what they do is, if you have a span of fiber, let's say 100 kilometers long, you can shoot in a huge amount of energy at a frequency where you're not transmitting, a very large amount of energy, and that causes amplification at the other frequencies due to the nonlinear coupling. Okay, and that's called Raman amplification. And through that, they can do a distributed amplification along the fiber. The alternative is to have amplifiers only, let's say, every 100 kilometers or 80 kilometers. But through this, they can do a continuous amplification. And if you look at the equations, continuous amplification causes only a multiplicative loss that stays constant across the fiber. In any case, if you go over many thousands of kilometers, you'll see rather than getting exponential loss going across, what happens is you can make the exponential loss go away and then just get additive noise coming across the fiber. And that also lets you send across much further distances with less noise overall. It's not too hard to write out the equation. You just write out the differential equation. You usually get an exponential loss by replacing. If you had an amplifier at every 50 kilometers, or every 10, or every 5, or every 1, or every 100 meters, and then you take the limit as this goes to 0, what you get is a better SNR performance as you get to the end by getting distributed amplification. And you can actually accomplish that in fiber using the nonlinearities themselves. Okay, so this is something that's very unique to fiber or other materials with the same kind of nonlinearity, which we'll get to. Then a big invention. So what happened here? Okay, so around this time, so people started building communication systems, right? And around this time, if you look at the textbooks and papers, so there's a well-known textbook by Benedetto and one of his colleagues, they're starting to run into limitations here, so they start using higher order modulation. So up to here, you see on-off keying, no phase shift keying, all is on-off keying. Suddenly here, books and people are starting to look at higher order modulation, coherent detection, and so on. And then bang, that all disappeared. Why? Because an amplifier was invented that could amplify signals across a much larger bandwidth than was possible before. And what that meant was communications could again become very inefficient for 20 years. You could send signals much faster, use much more bandwidth, and just use on-off keying. Okay, and so this killed basically research on communications again. So the communications theorists were no longer interested because they didn't play a role anymore. The physicists could use their old techniques on-off keying. And that continued until about the year 2000. Okay, then networking stuff started becoming important, so I'll mention that in a figure in a moment. These are multiplexers. So add drop. Optical means the device is electronic. That's the important thing for simplicity or to get down costs. You don't need to sit at DSPs with high speed. Add drop means you can add signals to the fiber at different frequencies or take them out through filtering. And the multiplexer just means, multiplexing signals and taking them out. So optical networking started to become more important. Then around this time, again, higher order modulation started coming back. So suddenly QPSK, BPSK started to become important again. And everyone, for a few years there was talk, oh, that's too expensive because we have to then use a coherent detector. But then people soon realized, no, it's not as expensive as we thought. And now everyone uses coherent detection. Then around the year 2010, people realized, well, standard single mode fiber, we're actually going to run out of bandwidth pretty soon. I'll show you a figure on the next page. And so since about 2010, the hot topic in optical fiber research, if you go to the OFC Optical Fiber Conference or ECOG, has been MIMO. Okay, MIMO, space division multiplexing. So here's an example. I'll show you another figure in a moment where you have 3 cores. Rather than having 1 core, you have 3. Or if you meld the cores together, you get multi-mode fiber. So doing individual cores is just a way, along the way to get multi-mode bigger cores. And companies like Corning and so on, I'm told they make this stuff. Okay, they can use that. Excuse me. So manufacturing that is really possible and is done. Okay, big question. What happens? So let me motivate a little bit why there has been interest in moving these things forward. So here's a plot that's probably from around 2012. It's a paper that Bob Kutch wrote together with Renee Messiandra. Bob Kutch is also at the labs. This is years from 1980 to 2020. Here's the traffic and capacity. The blue curve shows how demand is going, US core network traffic, and also predictions for the future. And you see there's a bump here. All of a sudden video starts becoming important, and not only data, basic data. The video starts to become important. And here's the capacity of commercial systems, of a single fiber per single fiber. Okay, at some point it goes up strongly. Where did this slope happen? It's because they had a broader bandwidth and started using wavelength division multiplexing, so frequency division multiplexing. They were able to ramp up the speed on one fiber very rapidly that way. Then came a knick, where the slope started going down. Where did those gains come from? These are now higher order modulation. Okay. And once space division comes, there's a hope we can come back to catch up to the demand again, of course. But it's not quite that far yet, right? So the system, the cost has to be brought down, but a lot of people are experimenting with this. A lot of patents are being written. Businesses, there's people ramping up for that business. That will come, I think, very quickly. The one big problem is, of course, you have to lay new fiber. That's expensive. Putting new fiber. In any case, traffic is predicted to grow at a faster pace than fiber capacity. And the first question you should ask, well, is that really a problem? After all, what I just showed was the capacity of one fiber. Right? And there's a lot of dark fiber around, so why is this a problem? And the problem is cost. The cost increases in proportion to the data rate if we start lighting new fiber. Every new fiber that you light, you need lasers, you need an amplifier, and so on. So costs go up proportionally to the bandwidth. So as a practical example, if you say, no, I want, maybe I should change this to 1 gigabit per second rather than 100 megabit per second link, well, the company will say, sure, pay us 10 times the amount, and they're probably not willing to do that. Right? And that will also break innovation. Why? Because it will make it less interesting for companies to come in, make new software pieces in the application itself. So this is something that could play a major role, and you could ask, perhaps eventually that will come. Maybe 10 years from now, the business cases will be very, very different. So what can we do? Well, first we have to improve the networks, the efficiency of running the networks. Perhaps that's a first step. And ultimately, though, we do have to worry about what is the fiber capacity. Okay. Any questions until now? I haven't. Again, if you
All these capacity calculations and so on are with classical approaches, not the quantum communication considerations or photon-based.
Right, so we should talk about models in a moment. So in the, maybe I can just talk a little bit about that now. So if you look at the information theory literature, people like Weiner were looking at these Poisson channels, but these models are for low energy, right? Individual photons. So very low rates too, right? Here we're talking about high energy, high rates. And for that, quantum considerations turn into Gaussian models again. Okay. So when you talk about optical channels, you very much have to talk about what regime are we talking about here. Like low energy, that's photon counting, space shots, stuff like that. You know, where you need very highly cooled devices to be able to detect individual photons accurately. Or are we talking high energy, high rate? Then we're back in the Gaussian noise model, but with nonlinearities. So it's not the classic analytic process.
So the quantum channel was for deep space, where it's very weak signal, send people back to exactly the same theory. Then cloud should have sun takes over and you go back to that and go back. Those are many particles.
Because you have many particles. Okay, so here's a picture. Okay, so let me talk a little bit about fiber channels. The standard single mode fiber channel looks something like this, a very small core and a bigger cladding. It carries, its size is chosen so that it carries one mode of light. One mode means actually 4 dimensions because there's 2 polarizations, and along each polarization you can send a sinusoid cosine. So it's actually 4 dimensions. So depending on terminology, some people will call a mode 2 or 4 dimensions. Here, single mode refers actually to 2 polarizations. So it has 2 complex dimensions, 2 polarizations. In most theory papers, often only 1 complex dimension is considered. In more general cases, interesting 2, but it turns out that the 2 polarizations are virtually independent. So studying 1 is the common approach. And a hot topic I mentioned is mono fiber. So people are talking about multi-core fiber with many cores, or if you take that to the extreme, you get multi-node fiber. So depending on which camp you're in, you either study this or you study this. It depends on how much signal processing you can do at the receivers, right? Here there's going to be less interference between the modes because you're separating them with cladding, whereas here you're going to have more interference. You'll have to worry about taking the signal apart and doing more signal processing. But otherwise, the principles are the same, right? It's space division. Okay, so here's the equation. So let me spend a little bit of time on this equation. This is this is an equation that's accepted as one standard model. It's a differential equation, which makes, I think, people who work on wireless sometimes a little uncomfortable, even though the wireless channel is also differential equation based. The only difference there is it's a linear differential equation. Once we have linear differential equations, we can create a lumped model. That's what we always do, right? We always just have x, y as hx plus y. But it's really a differential equation. Okay, now what happens here is there's an extra term that comes in, namely the nonlinearity, and that prevents us from making a lumped model out of this. We have to work with the differential equation. So what does this look like? Okay, so it's somewhat complicated. If you open a book on optical fiber, you'll always find the first few chapters derive this nonlinear Schrödinger equation model. And so what you have to start with Maxwell's equations on, in a circular, usually they talk about circular symmetry and it's one-dimensional, so that simplifies things. And then do some approximations that are considered accurate, and after you go through all that, you pop out with this model here. So what the model is the following. So the signal of interest is the E. So what E represents is the electric field in one polarization, so it's going to be a complex number that changes down the fiber, so it has 2 parameters, distance and time, or space and time. Okay, and it's a complex number that has a different value at every position in the fiber and at every time. Okay, and now we take derivatives with respect to space, distance, and with respect to time. And what the equation says is the distance evolution, so if I take a small little step in space, then the change in this electric signal is proportional to the signal itself. Okay, so this is a loss. So if you know your linear equations, then partial E partial Z equals minus alpha over 2E without anything else. It's just an exponential, results in exponential loss. Right? And down space, exactly. And then you have linear parts here, and these two parts here are second order dispersion and third order dispersion. And so what this is, if you remember your linear differential equations, you should do a Fourier transform of left and right. If you do a Fourier transform of derivatives, what do you get? You get j omega raised to the power of how many derivatives you have. So this term here in the spectral domain is an all-pass filter with quadratic phase. It's called chromatic dispersion. Okay, now, if you know your intersymbol interference theory, you know that to get no intersymbol interference, you need two things. You need a constant amplitude. Well, we have that here. It's an all-pass filter. But you need linear phase. Well, usually in wireless, we talk about it the other way around. There, the amplitude varies, but the phase is very linear. But here, it's the other way around. In fiber, the amplitude is constant, but the phase is very nonlinear, and that causes a lot of intersymbol interference. Usually, often people consider only the second order dispersion. We'll do that too, but I'll show you that the theory applies for any amount of dispersion, the upper bound that I will develop. Now, where it gets interesting, so everything up to here, if this was the model, only up to here, without the nonlinear, and this model is accurate at low launch powers, then you can make a lumped model, namely just a filter, all-pass filter with a quadratic and cubic phase, and you know how to solve this, right? OFDM, you can do it. You don't even need OFDM here, right? Well, you kind of do. There's a lot of intersymbol interference, so you should use OFDM, and you should adjust based on. That's one way. That's one way people do want to send over the optical fiber channels through OFDM, because that way you get rid of the ISM. The other way to do it is to use something called back propagation, because it turns out this equation is invertible nonlinearity. So you do fine sampling and you run the same signal backwards. But it's an all-pass filter, right? So you don't lose anything that way. But there's more that we can discuss about that. Where it gets interesting is this term here. Okay, this is called it's a third order nonlinearity. Now there should be a second order nonlinearity, and there is in general, but because of the symmetries of the fiber, that second order nonlinearity isn't there, okay, because it's a circular symmetry. So the one that plays the role is the Kerr nonlinearity. Now there's a parameter gamma that can be tuned by fiber designers. So people do design very high nonlinear fibers, very low nonlinear fibers, and so on. And then if you have distributed amplification, you would have noise, a little bit of noise that comes at every step of the fiber. If you didn't have distributed amplification, that noise would only enter every 80 kilometers or so. So in any case, this is the equation, and it's generally accepted as being a very accurate model of fiber propagation.
Including the noise model.
Including the noise model, Gaussian
This is
noise.
being
Absolutely.
verified.
I'm not an expert in it, but people generally accept this model. Well, it's Gaussian because it's amplified spontaneous emission that's caused by, I guess, quantum jumps, and you have many of them, and so it's considered to be a very accurate model. Where real fiber differs here is you'll notice every one of these parameters, alpha, beta 2, the second order dispersion, so the third order, and the gamma are generally frequency. They're generally frequency. Here I'm going to work with a model that does not have frequency-dependent parameters, and that's usually what theorists like to look at first. And I'll say a few more things about that. Looking at the frequency-dependent loss is important if you have a very broadband signal. Now, usually we focus only on frequencies or wavelengths where the loss is about 0.2 per kilometer, as well as. Yeah, any questions about this? This is probably unfamiliar to you if you've only worked with linear channels, right? These concepts will new. And getting used to this equation and its meaning takes a lot of time and experience. Okay, you can also do Fourier transforms again on both sides, and you have to worry about what does that mean for the nonlinearity and so on. But they're very interesting problems that you don't run across in wireless. Okay. So let me tell you now how people do simulations on this panel. And what they do, they just take this differential equation. What do? Well, we just break the thing into little pieces, take a long vector in time, which is oversampled, and run it through the differential equation. That's all people do. And this is called the split-step Fourier method for simulating waveform propagation down a fiber. What we do is we split the fiber into many small pieces, let's say of length delta z. We split time into many small steps, delta t, and what you do is now, if you take this signal, let's take the signal at a certain position in the fiber, so it's a long vector of samples, fine samples. What is loss and gain? Well, it's just a constant multiplication. What is dispersion? Well, we have to go into the Fourier domain and then multiply by a diagonal matrix that does phase shifts in a quadratic fashion or a cubic fashion, right? So I'm just going to do what every step is. Loss, linear, we go into the Fourier domain, multiply by a diagonal matrix. It's an all-pass filter, but with phase shifts. Take the inverse Fourier transform, and now we have to go through the nonlinearity. And it turns out that the curve nonlinearity operation you can show is the following operation. It also multiplies the signal by a diagonal matrix. However, it's special in that the phase shift is a quadratic function. The phase shift is proportional to the magnitude squared of the nth entry. So when you think of what the operation is here, if you look down your time vector, which we now have a time vector, you take every component, you take the square of that, and you shift its phase by that square multiplied by that gamma factor. That's what it is. That's that equation. And then you add noise, and you go to the next little piece of fiber. That's how people simulate this. Okay, now there's all sorts of tricks to make this simulation more efficient. For example, many people do a small linear step, one linear step, and then another small, one nonlinear step, and then a linear step. So you can split these things in different orders and ways to try to make things faster. But fundamentally, this is the model. And as delta z goes to 0 and delta t goes to 0, this simulates the differential. Now I like this. Why do I like this? Because it's a lumped model again. And I know how to work with lumped models. I'm an engineer, I don't like differential equations. I like these kind of diagrams. But then I will say, well, wait a minute, what is a differential equation? It is this diagram, right? So maybe I'm not so uncomfortable with differential equations after all, right? So that's exactly what the differential equation is. But since I have this block diagram, I can start working with it now. I can start doing bounds, okay, mutual information and so on. So that's what I'd like to do.
So this tracks the false
Yes.
strength. So when does the rate and multiplication come in?
I will talk about it in just a moment. Yeah. Any other questions? So it's important that you're a little bit comfortable now with this model. Okay, the only new piece is this nonlinearity, but it's kind of nice. It's a diagonal matrix multiplication with a phase shift that's a function of what's coming in. So it's invertible too, because I know if I look at the strength of every piece at the output, I know exactly how I have to invert the phase going back again. And that's important. It's going to be important. It's an invertible operation. So everything I do here forward, I can do back if there wasn't noise. But the noise screws things up. The important thing to realize, there's three things happening here. You know, there's the linear piece. This is all linear. There's a nonlinear piece, and then there's noise, and they all interact with each other. And because of this, you can't get a closed form solution for what happens at the output given what's at the input. There are no solutions. If it's noise-free, there are some solutions, namely the solitonics, right? So you can actually, if there was no noise, you could write out a pseudo-linear equation which basically breaks this equation into orthogonal components, like say OFDM does with linear systems. But it's not going to be the sinusoids anymore. The basis functions are going to be weird functions, solitonic functions. But you can still do mathematics with it. And so this was a remarkable development around the 50s and 60s. People started discovering, oh, wait a minute, this equation with the cubic nonlinearity and other equations that govern things like, you know, freak waves and so on, they have all that have this form. They're linear with one nonlinear component. Sometimes this is quadratic, sometimes cubic in different forms, but all these problems that you see have this kind of behavior. a lot of the problems we run into once you move a little bit out of linear, you have a pseudo-linear style of behavior.
So the noise is real, it's not because you left something out of the model. That's why I was asking you if it was measured.
The noise comes from amplification. The main noise, the Gaussian noise, comes from amplification processes. That's the dominating noise. So depending on where you do your amplifiers, or if you do it in distributed fashion. So if this was distributed amplifiers, you wouldn't put that plus in at every little piece. You only put it in, but with more noise every once in a while. Okay.
Why they call this Schrödinger equation?
The Schrödinger equation? Because it looks like a Schrödinger equation. If you look at it, it looks like one except with time and space swapped. But it's the same equation.
It's not a master equation derived from a quantum Schrödinger equation.
No, so this equation is derived from Maxwell's equations applied to
Okay,
this.
so another quantum in the derivation.
No. Well, are Maxwell's equations quantum? Well, I don't know. Maybe.
Not
really,
standard
I
quantum.
guess. Not really, but no, they're derived from Maxwell's equations. Other questions? So this is important, right? The model. Okay, so let me skip this. These are lower bounds, and it will take me too long. What do you want me to go through again? I want to get to the upper bounds. Maybe I can quickly say something about lower bounds. So I already mentioned one thing. There are no analytic lower bounds. So this is what I call a full model. Okay, already. It has linear part, nonlinear part noise. So people have computed lower bounds, and the way we've done it too is to do simulations. So there's two approaches people take for this problem. Approach A, since this seems to be too difficult, create a perturbed model from a linear model, and then develop information theory, communication theory. That's the more common approach. Approach number two is work with the correct model and do it via simulation. Okay, and that's the approach we mainly took. So in this approach, we worked with the full model, but did a simulation-based lower bounds. But then the question comes, well, which quantity should I study for a fiber? Should I study capacity? Well, in this model I just showed you, there's infinite bandwidth, so capacity is infinite. There's not much point. Or maybe capacity is infinite. We think maybe it's finite after all. I don't know. The second natural thing to do is what we do with linear channels is we study spectral efficiency, because you know that frequencies you can put one signal here, one signal here, and so on. So we should just try to normalize by the bandwidth we're using. But then, why is spectral efficiency important if the fundamental dimensions of this problem are non-frequencies, not sinusoids? Right? Maybe we should be looking at something Jim Massey called Shannon bandwidth rather than Fourier bandwidth. So he had a nice little paper that he wrote in 1995 where he distinguishes between Fourier bandwidth, sinusoidal, and Shannon bandwidth, which is the breakdown of the orthogonal dimensions of this signal. Well, I personally think even if Shannon bandwidth is the more fundamental issue, you will never get away from Fourier bandwidth because we'll have to do, well, up to now we always have to do some kind of electronic conversions, and all devices we use have bandwidth limitations, the fundamental one. So it's an interesting way, it's interesting to think about these two definitions of bandwidth because it's not so clear how to take them apart, which one is more important. And I think that's also why Jim was looking at this. He was interested in a very fundamental question. Okay, what is really the thing we should be normalizing against? Should it be sinusoidal dimensions or should it be other dimensions, right? It's an interesting question for nonlinear channels.
Forget the Slepian's channel lecture, I think,
That one
bandwidth. Was it
No.
looking at channel Fourier?
No, the Slepian was looking only at bandwidth, Fourier bandwidth at time. He wasn't considered a nonlinear. Yeah. So it's a little bit of a different kind of point of view, but it doesn't have to do with these two.
Is that if I take the model and think of it as solitons, right?
Yeah.
Then you have independent solitons. Is that related to some dimension?
Yes, that would be related to, but the dimensionality in these objects is a little weird. It's not the usual breaking into orthogonal and taking some dimension. Some strange things start happening in terms of scaling. So what you have to realize when you scale the eigenvalues, what you do is you change the shape of the pulse too, and that's what is unusual. We usually don't think of that. When we think about scaling something, we think of the same pulse getting bigger and smaller. Here it's bigger, but also spreads out in time. And so you can do stuff like that, but you have to be careful that you don't, take along too much baggage from your linear theory. You have to think very mathematically.
Why am I scaling the eigenvalues?
It turns out that when you launch a pulse into the fiber, there are certain quantities that are conserved. Those are the eigenvalues.
Of what we should remember?
Of a Lax style operator, as I'm not an expert on this.
This is Lax theory of
Yes, it is.
nonlinear wave.
Yes, that's exactly what it applies. That's what it was developed for, was exactly these equations. And so you have the eigenvalues are the one things that stay constant as we go along. Now, if I increase the eigenvalue, what happens is the pulse that corresponds to a certain, so if you take a certain eigenvalue, you get the solitonic pulses. Now, if I increase that, the pulse does get bigger, but it also squeezes the time. So it represents a new pulse, but that piece is what will go through on change. And you can put multiple of these solitons together to get higher order solitons. And they interact in strange ways too, but those things always stay constant.
The invariant.
Their invariance of the equation. Yeah.
That's why I'm suspicious because of this thing noise.
Well, the noise is separate, right?
Yeah, but if you do pure PD analysis, I don't know, see how the noise will come.
Noise enters the application because what happens otherwise there's loss.
Because I think it's coming because you try to think linearly on something that's totally nonlinear.
I'm not so sure. I think noise is separate from these issues. If I took the noise out and these equations,
But what does it do physically too?
due to spontaneous chain jumps of photons going up and down, electrons
Absolutely.
moving up and down.
If that's the noise model, then what you wrote down and it's called spherical equation must come out by some master approximation.
Well, usually when they begin to derive this equation, nobody considers noise. That noise is added afterwards. And
Or
that
comes
has-
out after.
Well, yeah.
We'll talk about that.
Yeah.
I haven't looked at it.
Okay. So this is called amplified spontaneous emission noise. So it's really a random process. If you like, this comes from quantum effects. Fundamentally, there are lots of them.
Yeah.
Is it additive term or the rate of decrease of the field? You have the rate of decrease, right, of the field on the left. And then there's an additive term on the right. Is that immediately clear if that should be the case?
Well, for distributed application, that's the accepted model. Intuitively, it makes sense to me. Every little piece,
Yeah,
a
so
little
you don't have the distribution.
Yeah. That's the model that's usually used, yeah. And it's based on random processes happening in the fiber due to amplification because you have photons affecting other photons here and you jump down randomly. And the Gaussian model is universally used.
This is a function of both time and space, right?
This is a function of both time and space.
So what does it mean to have noise that depends on time and space? We have a random field?
Well, the space should be pretty clear, right? If I have two amplifiers, one here and one here, there's going to be independent noise produced by those two
Sure,
amplifiers.
but it's continuous, right?
Yes, because here we're assuming that there's distributed amplification, so there's a little amplifier every meter, or 50 centimeters, or
Yeah, so it's a random field.
it would become a random field, perhaps, yes, okay.
Yes, but you only have a partial derivative on space. So
Sorry?
you are looking at the partial derivative, so you're only looking at the distance.
Yes.
So maybe that is some part of the background.
Well, T is that since you're taking the derivative with respect to T.
E is a function of two parameters,
Z
C
and
and
T.
T.
T and T, right?
Yes, that's right. I mean, I think what may be bothering you is that the infinitesimal distance.
No, it doesn't bother me at all, but I'm just curious.
Yeah.
So it's not the usual white noise process that we're talking in communication, but it's something much more complicated than that.
Well, the model is the usual white noise process.
In space and time?
In space and time.
Okay.
So the way this is
Then
simulated,
I'm at 99% sure this is a master equation on a quantum model.
it should be based on quantum thoughts, but the
When
way
you do in the master equation, you just look at the aggregate,
Yeah.
and then you basically, it's not exactly averaging, but it's the ensemble of moves.
Okay.
And that's what gives you this very good form. I will look at it, because then the solitons, maybe, I don't know, has anybody connected something to what you call sound dimension?
To what, to Shannon, well, yes, there's a lot of work going on.
They make this connection?
Yes, there's a lot of work. And right now, that's a hot topical area as to rather than using wavelength division multiplexing, use the Solitonic spectral theory. In fact, Mansour, who I had on the first page, he's the one who started all the recent activity on ODN.
Didn't they have works in the lab 15, 20 years ago on dispersion and solitons?
Mollenauer, yes. So Lynn Mollenauer, for those of you who are from the optical area, he was a super famous person who actually built systems like this. However, they were not competitive with wavelength division multiplexing because he could only send on-off signals, and there was a lot of timing. There's a lot of sensitivities in the solitons, so it's not even clear today. First of all, once you add noise, solitons are no longer solitons. I mean, they break down because of the noise. Once you have loss in the fiber, solitons are no longer solitons. So the solitonic behavior depends to a large extent on using Raman amplification, but that brings in distributed noise, which breaks things apart again. So it's not really clear, it's not 100% clear how well this will work. It does, it isn't that sensitive to, though you can actually send solitons down the fiber, and they build communication systems, and they work. But at that time, they weren't able to build them to be competitive with the simpler approach of just using wavelength. That's coming back again. So people are starting to get interested in solitonic transmission because now we have signal processing tools that are much more powerful than before. Perhaps we can do this in a different way. But it's not clear. It's not, no one knows, but there's a lot of activity on that right now. And in fact, like I said, Mansour is the person who started the whole recent accepted there. And it's really his PhD.
Can I ask a somewhat different question? This model is for optical fiber. Now, they talk about optical wireless.
Yes,
Where is,
a very different model.
very different, where is the fiber aspect of that, in that equation, that non-linearity?
Well, everything really, but the nonlinearity first and foremost. I mean, you can send with very high energy through space too, and you might ionize the air, and then you get nonlinear models again, but they have nothing to do with this model again. On the other hand, you can't forget this nonlinearity. What you're doing is you're building in nonlinearities using low-order approximations, and that's the natural approach, I think, for any nonlinearity, right? So maybe for air and ionizing, there's a second-order nonlinearity, and the equation will still look like this, a linear piece that you're very familiar with, just probably here with amplitude variations, Rowley fading, and all this stuff. And then here you'll get some nonlinearity that probably has a form that's either quadratic, cubic, or higher.
There are similar models of people.
There are similar models, but usually the ones people use are things like Rowley fading with different statistics than Rowley, right? So they're fading channel models at the low energy, and what limits your communication is more time variations first and foremost, and not so much the nonlinearity. Certainly, there's a lot of studies on that also.
They control the phase for free-phase lasers. Remember we had a lot of atmosphere. They became one of the lasers in atmosphere and so on.
And MIMO is a hot topic there too. People are trying to do MIMO processing here also.
But there's different ways.
Satellite communications and so on. It's a little different model. So I'm running really long. I'm wondering about what I should do. I would like to show you the upper bound still because it's very easy to get once you understand this. Okay, so let me show you the lower bounds, at least to motivate what I said at the very beginning. So these, what I'm showing you on this plot are curves. They're taken from a paper that Renee and several other authors, I was on this paper too, wrote, which I think is still the state of the art in capacity estimates for a standard single mode fiber with the model we had. In a network scenario, I could say a few more things about that. So this is the signal to noise ratio. It actually represents the launch power. So let's say a few things about that. anyways, this is the launch power, this is the spectral efficiency that we computed, including normalizing by bandwidth, right? So spectral efficiency with respect to Fourier bandwidth. And what you see here is the log of 1 plus SNR curve. This curve here is the linear channel capacity. And here you have the rates we simulated for various fiber distances, 500 kilometers, 1,000 kilometers, 2,000, 4,000, 5,000. A few things to be said about these curves. The first thing you notice is they hit a peak and come down. And so this bothers a lot of people. How can capacity increase if we have more energy? It's really bothers people.
Well, it's a lower bound.
Okay, so first, there's a few things to be said. First, it's a lower bound. Secondly, it's not a power constraint, it's the launch power. What it says is we're pumping in more power, but this still bothers a lot of people. Even if we're pumping in more power, can't we do something like, here's what you can do. You can put a heater beside your fiber. Siphon off some of the energy as heat, right? And then use only the remaining energy to send, and then we would get a flat curve, right? I mean, I'm serious, this has been argued in papers of that style. I mean, I'm overstating it, but really papers are being written of that.
But everything here is simulation or computation.
Sorry? The
What
simulation.
What happens if I'm simulating the real? Why do I see it? And why do I see that?
You do.
Because maybe the simulation should not be considered as a domain.
Right, I know people do measure bit error rates, and what they do is bit error rates under certain assumptions, of course, but what you see is bit error rates go down, and then you launch more energy, they go back up again. Now, of course, that has to do with the way we computed the lower bound. The way we computed the lower bound is using a mismatch decoder that assumes the channel after some processing is added, like a CLS channel, from that you can achievable rates. So there's a lot of things you can try to do to improve this lower bound. There's been a lot of studies on that. For instance, looking at correlations from symbol to symbol of noise and then taking that into account to improve your information rates. The gains have been very minor, and there's a lot of papers that have been written and they've improved things, but then when you look at the paper, you realize they didn't use the same model we did. They used not a network environment, but a single channel and so on. So I could say a lot more about these. I still feel this is the state of the art today. So even 6 years later, there's a lot of the scientific interesting question is: do solitons can improve this? This is done with wavelength division. Okay, that's an important thing. However, one should realize why this happens here. It has to do with the fact that once you hit a certain point in this nonlinear Schrödinger equation, the nonlinearities start kicking in. And once nonlinear states start kicking in, their main effect is to wrap phase around each other. And once phase wraps, and if it starts wrapping rapidly, you get a lot of bandwidth expansion. Once that bandwidth expansion happens and you normalize it around the signal, spectral efficiency just drops like a rock. And that's what's happening here. The signals are blowing out, and they blow out really rapidly. Now, whether solitons get around this is the interesting question. They do, right? Because they keep their shape.
Yeah.
Now you have noise.
But do you both might know the answer. Have they done coding for Soliton?
Yes, they're doing it now. It's happening.
Now or before?
Before, not so much.
So we don't know the performance of coding for Soliton.
No. So
Because the physicist, the first thing the physicist would ask is exactly that.
Yes, yes.
Because he will tell you, look, you find eigenvalues and different domain, that's linear approach. Let's go non-linear, full.
So people are doing that. So people are looking at studies. There was a paper that was appeared last week. Two papers, one from a group in Aston. They do a lot of work on this at Mansour, who's at Paris Tech. There are two papers on archive where they're doing higher order modulation on the solitons, but they're still not quite there yet. Like their spectral efficiencies are around here right now. Okay, and it's very hard to simulate out here because things get very fine. Energies are getting large, and you have to paste in a lot of symbols and so on.
In very broad terms, what is the structure that we would be looking for if we were to encode these signals?
The basic approach is to do something like OFDM. You assume these eigenvalues are independent, modulate them using phase and amplitude if you want to spread the signal. But anyway, most of it is done through phase modulation, because you can change the phase of the eigenvalues without changing anything else. That degree of freedom you always have. So effectively on every eigenvalue you do phase modulation. And then you do amplitude modulation for that on the different color shapes that you can choose. And that's what makes it starts getting difficult because you have to create packets of solitons. You can't send individual ones. Otherwise you have to do too much guard time. With WDM, you don't have this problem. You can send really long trains of sequences. You get rid of the spectral frequency loss due to time time. With solitons, you have to build packets up all together at once. And that, you need a lot of signal processing to do that. Okay, but complexity is a moving target, as we know already. So maybe this is possible. We're going on. I apologize, but I hope it's more interesting this way. These are lower bounds. Okay. Now let me get to the upper.
And I'll go to the bad bound.
Yeah, the bad bounds, the other side. The theory is going to be pretty easy, I promise you. This is going to be the last one. I need a few preliminaries. We have to talk about complex vectors and covariance matrices. Yeah. So let me talk about the covariance matrix of a random complex vector. That's what you know. There's something called a pseudo-covariance matrix where we, rather than taking the definition, we take the transpose. The X is called proper if this thing is 0. It's not so important. We're mainly interested in so-called circularly symmetric vectors. What I will need is a maximum entropy result. This is one that's, I think, well known. We have a vector X complex with a particular correlation matrix, and the entropy of that vector is upper bound by log of pi e to the L of the determinant of that correlation matrix with equality if and only if X is Gaussian zero mean and circularly symmetric. Then there's a well-known result. If I multiply any vector by a matrix, then the entropy of that product is the entropy of X plus 2 times the logarithm of the determinant of that matrix. The 2 comes because we have 2 dimensions. It's a complex vector. But if M is unitary, then of course this determinant is we get H of X. Then I need one thing that isn't so obvious to people who also people that have been looking at information theory. There's something called the entropy power. So Shannon defined the entropy power of a vector in terms of the entropy to be the exponential of the entropy, and then I'm bringing in here some normalizing constants. They're not so crucial. The important thing is e to the entropy of X. And Shannon proved an entropy power inequality, which is kind of interesting. It said, namely, if X and Y are independent, then the entropy power of a sum is always bigger than or equal to the sum of the entropy powers. That's a very non-obvious result, and it turns out you get equality here if things are Gaussian. There's a conditional version of this, which you can prove using concavity and convexity and Jensen's inequality. So the same result is true even if I condition on an arbitrary other member. This is the same all just with condition. And Jensen's inequality prove that once you know it. Okay, let's go back to our model and let's try to build a bound. Okay, I'm going to do 2 things. I'm going to focus on 2 basic quantities. Energy, pretty basic, and entropy, less obvious, but okay, also basic in some ways if you knew what entropy really was. And my claim, the basic insight is 2 observations. First of all, the first one's kind of obvious. The linear step of this propagation equation, this linear part, it conserves energy and entropy. Because everything is unitary here. F is unitary, Fourier transform. Diagonal phase shift is unitary, D is unitary, so obviously energy is conserved, and from what we just saw, so is entropy. Unitary matrix multiplication. So this step conserves these 2 quantities. The new result is this last one here, but the nonlinear step I claim also conserves energy. Now energy was known. It seems that the fact that entropy is conserved by the nonlinear is good. Physicists I talk to say, oh, that comes as a surprise to them. I never thought of that. Of course, their first question is, what do you mean by entropy? Because they understand entropy a little differently than the way we do. Even though, of course, they're effectively the same thing that they talk about too, right? It's just they don't look at it from that perspective.
expected.
And I think that's the key result, that this box conserves entropy. It also conserves other things, by the way. It conserves momentum. It conserves a whole bunch of other physical properties. So they knew that in certain second order statistics and third order, fourth order statistics. Okay, why is this key? Because I'm going to use it, and here's a proof, by the way, but it shouldn't come as a big surprise. Remember what this box does. It takes this vector, every entry, what you do with every entry is you take the amplitude. So here, what comes out of the box is just going to be A, amplitude, e to the j, the argument A, plus some deterministic phase shift that's a function of the amplitude coming in. And then if we rewrite this, I can write this using the chain rule. By changing coordinates, I have to add an expectation of the logarithm. Anyway, I just get the entropy of the amplitude and phase plus a correction term. And I can use the chain rule to write this as the entropy of A plus the entropy of arg A plus f of A given A. But once I know this, I can just subtract that off, right? Because adding something doesn't change entropes. And then I just put everything back again. Okay, so it conserves entropy. Now, why does conserving entropy work? Because we have an entropy power inequality. Use that to do a balance. So let's do the energy recursion. Well, what happens? As this vector goes across the linear step, no change in energy. As it goes across here, no change in energy. Oh, as noise, energy goes up, right? By the little bit of energy that gets added. And so the energy after k step is energy of launch times the number of steps I have times the variance of the noise at every step. Now, if I have distributed noise, that variance decreases, of course, with every length of the step goes down, right? But anyway, I can add them up for finite step sizes and then take limits afterward. And then now I can apply the maximum entropy theorem. Namely, if I know the energy of this vector, that's upper bounded by the log of pi L, the determinant of the covariance matrix of this. But then we have Hadamard's inequality that says, oh, the determinant of a matrix is upper bounded by the product of the diagonals. And now I can use Jensen's inequality to take that sum inside, and the sum of the diagonals is just the launch energy, the final energy of the whole signal. Okay, so I get an upper bound. That one's kind of straightforward. It's the maximum entropy result. What I need now is a lower bound on conditional entropy. Right? But how do I do that? Well, I use the entropy power inequality. So let's look at the entropy, the entropy power at step k plus 1 conditioned on the launch signal is upper bounded by, if I just go back one step across the noise, is lower bounded by the entropy power here plus the entropy power of the noise, which is just noise energy. And I just do this k times, so I just get k and L, so the entropy power of the output, given the signal at the input is lower bounded by k and by L. Now I just take down the exponential, I get log of pi k L, and I just, subtract this term off from this term, and lo and behold, you get L log of 1 plus this. New result.
So if the model is correct, validated, then the reason that this upper bound is loose, tell me if I'm wrong, is because one of the two steps that we did the bound, we either had a mother or a cross. So Jensen is bad.
We don't know if it's loose.
Huh?
We don't know if it's loose. This could be the capacity.
But is the Hadamard loose bound?
Maybe.
It's not a very good bound, you know. I mean,
It works.
that's for method.
It works for linear time.
No, but it's not a linear time.
No, but it doesn't mean the capacity is lower than the launch one. We don't know. Right
No,
now.
I mean, logically thinking, I'm thinking the following. He has a model that is accurate and tested, right?
Okay.
Right. Now he's trying to develop an upper bound.
I know.
He does it by a sequence of steps.
Yeah.
So there must be something in the math that's loose.
Well, unless it
Not
isn't
in the
loose.
physics.
Unless it isn't loose.
But
I
we
mean-
know some of these bounds, okay?
No, but we don't know if it's loose. Right now, this is the best upper bound. These are the best lower bounds. There's a
I mean,
world.
the experiments
There's a
don't-
world in between, and we have no idea.
The experiments do not show anything, I see. Okay.
It really is that way. You really don't know whether capacity goes, spectral efficiency goes down or not. We really don't know. Nobody knows. It's a complete hole. And before this bound, that black curve wasn't even there. The upper bound was infinity. I think that's a good improvement.
But from experiments and measurements, what kind of
Yes.
spectral efficiency?
Yes. So you can get to this linear curve at lowest R. That's achievable, and even experiments show that you can do that. Okay, but I will say there were large research grants which were funded on the premise that you could improve the capacity of hyper beyond block one plus SNR. There were several large-scale research projects funded on it.
And it didn't,
Well, at the time it wasn't, now it's the way it is, right? So it's legitimate, right? But even today, we don't know, and a lot of people want to see, at least inside this model, they would very much like to see, to get rid of this drop, that if we launched more power within the model, I mean, a real fiber will have limits. It turns out that if you increase the launch power of the way it was done today by, I don't know, if it's 10 or 20 or 30 dB, fiber will melt. It's just gonna break apart, and of course, then the capacity will come down. But you'd like to know, at least in the mathematical model, whether in principle, as you increase power, can you keep pushing the capacity higher? Now, there's diminishing returns, obviously, because even if I increase here, by a factor of another 10, I'm only going to get a percentage-wise the gain of 20 to 30%. That's probably not really worth it, but from a mathematical perspective, it's interesting. And down here, it's more worthwhile. If you're at 8,000 kilometers, if we can move out to either way, I can double the rate. That's commercially important, very important. But there's a lot of interesting questions. So that's the last part of my But the last part I want to talk about is a little bit of discussion on these things. I could say a lot more about it. So what we do to compute this, and do the last step, is we normalize by L. And you can argue, why should we normalize by that L? That turns out to be the time bandwidth product for what I'm doing, but it turns out that if you look at the bandwidth of the signal propagating on fiber, it can expand, contract, expand, contract. So you have to be a little careful about what your definition of bandwidth is. It's not so obvious. I think this is the only reasonable definition. And when I've thought about it, no one's been able to convince me otherwise. Okay, maybe we're not interested in spectral efficiency, maybe we're interested in capacity. Well, then we can get upper bounds. If I just multiply whatever bandwidth you have, it's going to be B times upper from there, so it's upper bound too. What about MIMO? Turns out the bound is completely valid there again. Why? Because all models in MIMO, what they do is the linear piece is just more complicated, and the nonlinear piece is more complicated. It's always a unitary transformation. Okay, so the bound carries through for all multi-mode, multi-core fibers. It's just going to be on a per mode perspective. Okay, polarization goes through, because all the standard models always have the linear piece being unitary, and the nonlinear piece just having the same kind of structure, returning phase shifts, which are a function of time, so we can go through. Third order dispersion works, unitary transformation. Delayed Kerr effect, you get to really high speeds, getting the delayed effect that also goes through because of conditioning. So it's a very generic bound. It works for distributed application or lumped, right? Because this is an important observation too, I can shift these boxes around any which way I want. I can draw the noise at the end, and it's the same bound. I can distribute the noise across. I can move the nonlinear around as I will, and the bound stays the same. I can move the linear part around as I wish, and it always stays the same. I mean, it's a very, clearly very robust bound, right? All kinds of constructs. So people talk a lot about phase conjugation channels, where what you use to build a fiber channel, you conjugate the phase down. Nothing changes, it's just a unitary transform. You're still bounded by this. Of course, there you hold it the peak further out, but I think that's necessary. Okay, most interesting to me right now is frequency and bringing in frequency-dependent loss. It could be that you can increase. So if you have frequency-dependent loss for linear channels, you know the result is Shannon's water filling. So water filling. Here it's not clear. Because the nonlinearity shifts frequencies around, it could shift signal frequencies at high loss to ones of low loss. Now you could potentially beat the linear channel capacity. Right? There's some potential for that happening. But I think that's a very interesting problem area. I don't have a good way of extending what I did here to frequency loss, not in the way I'd like. Okay, there was some recent excitement. There was a paper that did what we did here, just in reverse order. We can apply the entropy recursion to the unconditioned entropy power and the energy recursion to the conditional one to get a lower bound. Talk about that. It doesn't quite work as well as you think it might. So that's a little. Okay, so that brings me to the last slide. Conclusions. Nonlinear cascade models, I think, are fun to study. They're differential equations. So they're a lot of work going on in molecular communication there now, other areas. I think it's a good direction to learn about these differential equation-based communication. Spectral efficiency, signal fiber, linear polarization, it's log this harm, there's extensions, Tosca, long temperature, version related to uniform loss, linear filters. Okay, say more about that line. If the linear nonlinear states conserve energy and entropy, Gaussian noise, Gaussian whites, these are standard multimodal Fourier models. What's more difficult is better bounds. Of course, I'd like to get a bound that actually decreases also quantifier. If it's possible, I don't know yet. It looks tough because you really have to get into the nitty-gritty of nonlinearity. Frequency dependent loss should hopefully be a little easier. And I'm also interested in the network information, of course, not just.
But network information too, but I mean, fibers are like dedicated links, so anything like network coding or what would the...
Yeah, interference line, that kind of thing. So this is the way we operate, the idea of the way they want to operate networks is that you launch, say you have two transmitters, it's really an interference channel model. You have two transmitters, two receivers, and what you do is you send your signal down one frequency, you choose one wavelength, the other person gets another dedicated wavelength.
So there's no link by link?
No, that's right, yeah. If you do it link by link, ultimately that's the way things will go, I think. It will be link by link, but now we're talking maybe decades into the future. Right now that's too expensive. You need to do electronic optical conversion, you need very high powered signal processors, that just sucks too much energy. You'd like to build an optical fashion. Doesn't mean that's not the way we're going to do it in the future.
It's more end-to-end, right?
It's end-to-end, yeah.
You get by cost.
Out of cost reasons, but eventually, that's more efficient to do it than to link, and then maybe you don't have those nonlinearity issues as much anymore.
You better know in physics what happens when...
Yeah, and build real routers and so on, but it's still way too complex today to build it that way, right? But eventually, I think it might have to go that way. Thank you for your attention.
Thank you very much.